Good afternoon, class. We are now in week 10 of our discussion here in Elementary Statistics and Probability. Before we start, I just want to remind you about the mission and vision of Tanawan Institute. Let us know first what are the objectives of this topic. So after completing this topic, the student should be able to determine and identify what are the two areas of concern of inferential statistics, and also to determine the approximate size and calculate the sample size required to estimate a population mean and a population proportion given a desired confidence level and margin of error. Our topic for today is all about estimation.
Statistic, the science of collecting, presenting, and analyzing and interpreting data. Descriptive statistic, describe the characteristic and properties of a group under investigation. Inferential statistic, methods of making inference and drawing conclusion about the characteristic of larger group by studying in small representatives. Inferential statistic, a series of procedure in which the data obtained from samples are used to make a statement about some broader set of circumstances. Two areas of concern of inferential statistics. Estimating population parameters. Point estimation. Using a sample statistic to estimate a population parameter. Interval estimation. Estimation of the amount of variability is a sample statistic when many samples are repeatedly taken from a population. Hypothesis testing, the comparison of sample result with a known or hypothesized population parameter. Estimation, the two types of estimation. Point estimation, a single number or central tendency. Interval estimation, a range of numbers. Example, you take your car to your local car dealer's service department and you ask the service manager how much it will cost to repair your car. If the manager say it will cost you 25,000 when she is providing a point estimate. If the manager say it will cost somewhere between 20,000 to 30,000, she is providing an interval estimation. Estimation, null hypothesis and alternative hypothesis. A hypothesis is an approximate explanation that relates to the set of facts that can be tested by certain further investigation. Null hypothesis state that there is no exact or actual relationship between the variables. Alternative hypothesis state that there is a statistically significant relationship between two variables. Confidence interval or CI. The confidence interval is a range of values that likely to include a population value with a certain degree of confidence. It is often expressed in percent, whereby a population means lie between an upper and lower interval.
1 minus alpha times 100% t interval for the population mean. So the formula for the confidence interval in words is sample mean plus minus t multiplier times standard error. How is the t multiplier determined? As the following graph illustrates, we put the confidence level 1 minus alpha in the center of the t distribution. Then since the entire probability represented by the curve must equal 1, a probability of alpha must be shared equally among the two tails of the distribution. That is, the probability of the left tail is alpha over 2, and then the probability of the right tail is also alpha over 2. If we add up the probabilities of the various parts, alpha over 2 plus 1 minus alpha plus alpha over 2, we get 1. So the t multiplier denoted as t sub alpha over 2 is the t value such that the probability to the right of it is alpha over 2. It should be no surprise that we want to be as confident as possible when we estimate a population parameter. This is why the confidence level are typically very high. The most common confidence levels are 90%, 95%, and 99%. The following table contains a summary of values of alpha over 2 corresponding to these the common confidence levels. And take note that the confidence coefficient is merely the confidence level reported as a proportion rather than as a percentage.
Level of significance or p-value. The level of statistical significance is often expressed as a p-value between 0 and 1. The smaller than p-value, the stronger than the evidence that you should reject the null hypothesis. A p-value is less than 0.05, typical less than or equal sign 0.05 is a statistically significant. P-value higher than 0.05 is not statistically significant and indicates strong evidence for the null hypothesis. Margin of error. The margin of error of a statistic expressing the amount of random sampling error in the result of a survey. How many percentage points your result will be differ from the real population value. Margin of error decrease when sample size increase. Confidence level. It is estimated probability that a population estimate lies within a given margin of error. Type 1 and Type 2 errors. In the context of testing hypotheses, there are basically two types of errors we can make. Type 1 and Type 2 errors. Because a p-value is based on probabilities, there is always a chance of making an incorrect conclusion regarding accepting or rejecting the null hypothesis. Example of margin of error and confidence level. Company X conduct a survey of customer and finds that 50% of the respondents say its customer service is very good. The confidence level is cited as 95 and margin of error is 3%. This information means that if the survey were conducted 100 times, the percent who say service is very good will range between 47 and 53%. Most 95% of the time.
Sample size. The formula to calculate sample size. If the population size is finite and known, we're going to use the Slobin's formula, which is n is equals to n over 1 plus n e squared. And n is equals to sample size. The capital N is the population size and E is the margin of error. For example, in study, size of the population is 10,000. The margin of error is assumed to be 2%. So using the Slobin's formula, n is equals to 10,000 over 1 plus 10,000 times 0.02 square. So it is equals to 10,000 over 1 plus 10,000 times 0.004. And also it is equal to 10,000 over 1 plus 4 equals to 10,000 over 5, and we have our final answer, which is 2,000. Therefore, your representative sample size is 2,000 out of 10,000. Here's the sample problem number 1, determining sample size. We want to do a survey of employees of the municipality of Rizal on how they use computers at work if the total population is 2,500, and if you want to work with a 95% confidence level, what will be the sample size? Using the Slobin's formula, so we have here n is equals to 2,500 over 1 plus 2,500 times 0.05 square. And then the answer for this sample problem will be 344.
What is the difference between an estimator and an estimate? An estimator is a function of a sample data to be drawn randomly from a population, whereas an estimate is the numerical value of the estimator when it actually computed using from the specific sample. Estimator. Sample statistic used to estimate a population parameter is called an estimator. An estimator is a rule that tells us how to calculate the estimate, and it is generally expressed as a formula. What are point estimators? Point estimators are the functions that are used to find an approximate value of a population parameter from random samples of the populations. They use the sample data of a population to calculate a point estimate, or a statistics that serves as the best estimate of an unknown parameter of a population. Estimation of the population mean stratified random sample. An unbiased estimator for the variance of the overall population mean is variance of overall population mean is equal to 1 over n squared times the summation of the product of n squared sub j and sigma sub mean sub j, where the variance of overall population is equal to s squared sub j over n sub j times total population sub j minus n sub j over total population sub j minus 1. Provided the sample size is large A100, open parenthesis 1 minus a close parenthesis %, confidence interval for the population mean for stratified sample is sample mean sub st minus j sub a over 2 times sigma sample mean sub st is less than the population mean less than plus c sub a over 2 sigma sample sub mean st. Estimation of the population total stratified random sample. An unbiased estimation procedure for the variance of the estimator of the population total yields the point estimate. So, the product of n squared and sigma squared sub sample mean sub st is equal to the summation of the product of n squared sub j and sigma squared sub sampled mean sub st. Provided the example size large number 100 quantity of 1 minus a %, confidence interval for the population total for the stratified random sample are obtained. N sample mean sub ST minus J sub A over 2 times N sigma sub ST is less than N population less than N simple mean sub ST plus J sub A over 2 times N sigma sub ST. Estimation of the population total stratified random sample. Suppose that random sample N sub J individuals from strata containing N sub J individuals, J is equal to quantity of 1, 2, so on, K, are selected, and that quantity to be estimated is the population total N sub mu. An unbiased estimation procedure for the population total N sub mu yields the point estimate. N times sample means sub ST is equal to the summation of the product N sub J and population mean sub J.
Estimation of the population proportion stratified random sample. Suppose that random sample of N sub J individuals from strata containing N sub J individuals, J is equal to 1, 2, K are obtained. Let P sub J be the population proportion and P sub J the sample proportion in the JTH stratum. If P is the overall population proportion, an unbiased estimation procedure for P yields is estimate population sub ST is equal to 1 over N times the summation of the product of N sub J and estimate proportion sub J. Proportional allocation sample size. One way to allocate sampling effort is to make the proportion of the sample member in any stratum the same as the proportion member in the stratum. If so, the JTH stratum is N sub J over N is equal to the population sub J over the total population. The sample size for the JTH stratum using the proportional allocation is N sub J is equal to the population sub J over the total population times N. Estimation of the population mean stratified random sample. Let random samples of N sub J individuals should be taken from strata containing N sub J individuals, J is equal to 1 to K. Let the summation of N sub J is equal to the population and the summation of N sub J is equal to N. Denote the sample means and variances in the strata by X sub J and S squared sub J and the overall population mean by mu. An unbiased estimator of the overall population mean mu is sample mean sub ST is equal to 1 over N times the summation of the product of N sub J and sample mean sub J. Estimation of the population proportion is stratified random sample. Provided the sample size is large 100, open and close parentheses, 1 minus A% confidence intervals for the population proportion for stratified random samples are obtained from the estimate proportion sub ST minus Z sub A over 2 times sigma sub estimate proportion sub ST is less than P less than estimate proportion sub ST plus Z sub N over 2 times sigma sub estimate proportion sub ST.
The field of statistical inference consists of those methods used to make decisions or to draw conclusions about population. Statistical inference may be divided in two major areas: the parameter estimation and the hypothesis testing. So we are going to focus on parameter estimation, or what we called point estimation. For example, suppose that a structural engineer is analyzing the tensile strength, a component used in an automobile chassis. Since the variability in tensile strength is naturally present between the individual components because of difference in raw materials, batches, manufacturing processes, and measurement procedures. The engineer is interested in estimating the mean tensile strength of the components. In practice, the engineer will use sample data to compute a number that is, in the some sense, a reasonable value or guess of the true mean. So the number is called the point estimate. A point estimator of some population parameter theta is a single numerical value of a statistic p. The statistic p is called point estimator. So the phi will be used in replacement to the theta. So as an example, suppose that the random variable x is normally distributed with an unknown mean. The sample mean of the x bar, or the notation for sample mean, is a point estimator of unknown population mean, or mu. Thus, if x sub 1 is equal to 25, x sub 2 is equal to 30, x sub 3 is equal to 29, x sub 4 is equal to 31, the point estimate of mu of population mean is sample mean is equal to 25 plus 30 plus 29 plus 31 all over 4 is equal to 28.75. So our mean is 28.75. So the point estimator, the x bar of the sample mean will be the value of the population mean. Similarly, if the variance is also unknown, a point estimator for the variance is the sample variance s squared, and the numerical value can be computed as s squared is equal to x sub 1 minus x bar, or sample mean, squared all over n minus 1. So if we're going to substitute the x sub 1, or the number 25, 30, 29, and 31, then minus to the sample mean, the 28.75, then squared. So it will be 25 minus 28.75 squared plus 30 minus 28.75 squared plus 29 minus 28.75 squared plus 31 minus 28.75 squared all over 4 minus 1 is equal to s squared is equal to 6.9167. So this will be the point estimator for the population variance. We may have several different choices for the point estimator of a parameter. For example, if we wish to estimate the mean of the population, we might consider the sample mean, the sample median, or perhaps the average of the smallest and largest observation in the sample as point estimation. In order to decide which point estimator of the particular parameter is the best one to use, we need to examine their statistical properties and develop some criteria for comparing estimator. An estimator should be close in some sense to the true value of the unknown parameter. And we say that phi is an unbiased estimator of theta if the expected value of phi is equal to theta. Sometimes there are several unbiased estimator of the sample population parameter. For example, suppose we take a random sample of size n is equal to 10 from a normal population and obtain the data 12.8, 9.4, 8.7, 11.6, 13.1, 9.8, 14.1, 8.5, 12.1, and 10.3. The sample mean will be x bar is equal to 12.8 plus 9.4 plus 8.7 plus 11.6 plus 13.1 plus 9.8 plus 14.1 plus 8.5 plus 12.1 plus 10.3 all over 10. So our sample mean will be equal to 11.04. So the next one, we're going to find the sample median. So the sample median will be arranged to the data to lowest to largest. So it will be 8.5, 8.7, 9.4, 9.8, 10.3, 11.6, 12.1, 12.8, 13.1, 14.1. In getting median, we're going to find the middle values. So this is an even number. So we're going to find the two middle values, which is 10.3 and 11.6. So we're going to find the sum of the two middle values, then divide to 2, then it will be equal to 10.95. And then find the 10% trimmed mean will be x bar is equal to 8.7 plus 9.4 plus 9.8 plus 10.3 plus 11.6 plus 12.1 plus 12.8 plus 13.1 all over 8. Then it will be equal to 10.98. Since there can be more than one point estimate, we need a method to select among unbiased estimators. Variance of a point estimators. Suppose that phi1 and phi2 are unbiased estimators of theta. This indicates that the distribution of each estimators is centered at the true value of theta. However, the variance of these distributions. On this figure, we have two probability distributions graph. The one had smallest variance while the next one had large or wide variance. The center were the true value of data. Both of them are unbiased estimators. So we can examine that phi1 is the best to use as estimators. Variance of point estimators. If we consider all unbiased estimator of the one with the smallest variance is called minimum variance unbiased estimator or MVUE. In situation in which we do not know whether MVUE we could still use as minimum variance principle to choose among competing estimators. Suppose, for example, we wish to estimate the mean of a population not necessarily a normal population, we have a random sample of n observation and we wish to compare two possible estimator for mu, the sample mean, and a single observation from the sample. So, for the sample mean, the variance is equal to sigma square over n, while the variance of any observation is sigma square only. So, when your n is greater than or equal to 2, then the variance for sample mean will be less than to the variance for the single observation.
Standard error of the sample mean SWR and SWOR cases. It is calculated by taking the standard deviation and dividing it by the square root of the sample size. It gives the accuracy of the sample mean by measuring the sample-to-sample variability of the sample means. It describes how precise the mean of the sample is an estimate of the true mean of the population. As the size of the sample data grows larger, the standard error of mean decreases versus the standard deviation. Hence, as the sample size increases, the sample mean estimates the true mean of the population with greater precision. In contrast, it increasing the sample size does not making the standard deviation necessarily larger or smaller. It just becomes a more accurate estimate of the population standard deviation. For example, we will get the standard error of height of Alex, Lito, Isin, LJ, and Brian. So first, we will get the mean. In getting mean, we will add all the heights, then we will divide it by 5. So our mean is equal to 162.4. Then after getting the mean, we will subtract the height and mean to get the deviation. Then after getting the deviation, we will multiply it by itself to get the standard deviation. So, after getting the deviation that is multiplying by itself, we will add it. So, it is equal to 272.7. We will divide it by 4. So, it is equal to the square root of 68.175. So, the square root of 68.175 is equal to 8.257. So, that is our standard deviation. In getting the standard error, the formula is standard deviation over the square root of n. So, 8.257 over the square root of 5. So, the square root of 5 is 2.236. So, 8.257 over 2.236 is equal to 3.693. That is our standard error. Symbols of parameter and its estimator. Parameter is a statistical constant that describes a feature about a phenomena, population, probability mass function, or probability density function. The parameter are the unknown values of entire population such as the mean and the standard deviation. Samples can estimate population parameters, but their exact values are usually unknowable. Parameters are also Q is the complement of sample proportion, X is the sample mean, E is the sample proportion, 1 minus A is the confidence level, CI is the confidence interval, LCL is the lower confidence limit, M is the margin for error, N is the sample size, NHTS is the null hypothesis test of significance, S is the sample standard deviation, SDM is the sampling distribution of mean, hypothetical probability model of the standard error of mean, SEP is the standard error of the proportion, UCL is the upper confidence limit, SEM is the standard error of mean, A is the alpha level, mu is the expected value of the proportion, and the standard deviation of parameter. The binomial probability of success P is also called the population proportion. The expected value mu is also called the population mean. The standard deviation is also called the population standard deviation. Points estimate a single joints that are used to infer parameter directly. For example, sample proportion p hat is the point estimator of sample proportion. Sample mean x bar is the point of the expected value or the proportion mean. Then the sample standard deviation S is the point estimator of standard deviation parameter.
General formula for all confidence interval is point estimate plus minus critical value times standard error. So suppose the confidence level is equals to 95%, also written as 1 minus alpha is equals to 0.95. A relative frequency interruption, in the long run, 95% of all the confidence interval that can be constructed will be contain the unknown true parameter. A specific interval either will contain or will not contain that true parameter. No probability involved in the specific interval. Assumptions. Population standard deviation is known. Population is normally distributed. If population is not normal, use large sample. So confidence interval estimate is equals to mean plus minus c standard deviation over square root of n, where c is the normal distribution critical value for a probability of alpha over 2 in each tail. Consider a 95% confidence interval. 1 minus alpha is equals to 0.95. Our point estimate is the center of the bell curve, which is 0, and we have the lower confidence limit and upper confidence limit, which is the positive and negative 1.96 from the C table, and of the left and the right tail, which is alpha over 2 is equals to 0.025. Commonly used confidence level are 90%, 95%, and 99%. So as you can see in the table presented, we have here the confidence level, confidence coefficient, and the C value. Sample problem number 2. A sample of 11 circuits from a large normal population has mean resistance of 2.20 ohms. We know from past testing that the population standard deviation is 0.35 ohms. Determine a 95% confidence interval for the true mean resistance of the population using the formula. So we have here now 2.20 plus minus 1.96 times 0.35 over square root of 11, which is equals to 2.20 plus 0.2068 is equals to 2.4068. And also we have 2.20 minus 0.2068, which is equals to 1.9932. So we are 95% confident that the true mean resistance is between 1.9932 and 2.4068 ohms. If the population standard deviation is unknown, we can substitute the sample standard deviation. This introduces extra uncertainty since S is variable from sample to sample, so we can use the t distribution instead of the normal distribution. Assumptions. Population standard deviation is unknown. Population is normally distributed. If population is not normal, use large sample. Use students' t distribution. Confidence interval estimate is equals to mean plus minus t sub n minus 1 standard deviation over square root of n, when t is the critical value of the t distribution with n minus degrees of freedom and an area of alpha over 2 in each tail. Students' t distribution. The t is the family of distributions. The t-value depends on degrees of freedom. So we have here the number of observations that are free to vary after the sample mean has been calculated. Degrees of freedom is equals to n minus 1. Degrees of freedom. Number of observations that are free to vary after the sample mean has been calculated. For example, suppose the mean of three numbers is 8.0. So let x sub 1 is equals to 7, let x sub 2 is equals to 8, then what is the x sub 3? If the mean of these three values is 8.0, then the x sub 3 must be 9. For example, x sub 3 is not free to vary. Here, n is equals to 3, so degrees of freedom is equals to n minus 1 is equals to 3. 3 minus 1 is equals to 2. So, two values can be any numbers, but the third is not free to vary for the given mean. Students' t distribution. Let n is equals to 3. Degrees of freedom, n minus 1 is equals to 2. Alpha is equals to 0.10. Alpha over 2 is equals to 0.05. So, as you can see, we have here 2.92 from the upper tail area of the alpha over 2, which is 0.05. In this table, which is the t distribution values with comparison to c value, we have here the confidence level and the t 10 degrees of freedom, 20 degrees of freedom, and 30 degrees of freedom with corresponding with the c value. So take note that t to a random sample of n is equals to 21 has the mean of 50 and standard deviation 8. We're going to form a 95% confidence interval for population mean. So the degrees of freedom is equals to n minus 1 is equals to 24. So the t multiplier will be equal to t.025 and 24, which is equals to 2.0639. So we have here the confidence interval is mean plus minus t multiplier standard deviation over square root of n, which is 50 plus minus 2.0398 over square root of 25. So we have our final answer, which is 46.698 and 53.302.